Hey everyone, and welcome to this session as part of We Do AI. This one is about enhancing RAG, so Retrieval Augmented Generation, with the help of knowledge graphs and one of the more recent models from OpenAI, which is GPT-4o mini. And this is an introductory level presentation. Now, my name is Geert Bake. I work for Kronos in Belgium as an Azure and AI architect. I'm also a Microsoft Azure AI MVP. And of course, you're more than welcome to check out my blog and my YouTube channel or get into contact via X or preferably LinkedIn. Now, what's on the agenda? Well, first of all, we'll take a look at what is RAG exactly, so Retrieval Augmented Generation. And then we'll quickly go over into what knowledge graphs are. I'm going to explain the basics of knowledge graphs and then take a look at how we can potentially, and that's an important word, potentially improve RAG with knowledge graph. And then to end this presentation, we're going to take a look at Microsoft's GraphRAG solution, which is an open source solution based on a paper they have published about this. So let's get started and let's take a look at LLMs and RAG. What is this all about? Now, in this presentation, I'm not going to explain in detail what LLMs are and what they do. You probably use them either daily or several times a week. But we do know that these large language models are trained on a large amount of data from the internet. And this training and the training data provide it with two different things, right? It provides it with knowledge on how language works, and that in multiple languages, so English, Dutch, French, and so on. But it also learns about or stores information about all the things it has seen during the training. And that's why we can ask questions like this one, a physics question, explain what gravity is. It'll answer this from its knowledge it has been trained on. And basically this information is stored within the weights of that model. Now, that's all fine for general questions, and it might be wrong as well. We do know that sometimes it gets things wrong. But when you start asking questions like in a business context, for example, like you're building a chat assistant, and I want to ask a question how to park at Kronos, well, it doesn't actually know that. It hasn't seen that. It doesn't have it in its training data. It's going to give me a little bit of text that basically means I don't know. And in this case, it doesn't even listen to if I'm saying, if you do not know, say it. It doesn't actually adhere to this because it wants to give me with some information anyway. And that's, of course, something that we want to solve. Now, how do we solve that? Well, we actually solve that using what we call Retrieval Augmented Generation. And without knowing what's happening in the background, look at the following thing here. When I'm asking how to park at Kronos, what I actually will do as a developer, I will take that initial question, so just that question, how to park at Kronos, and I will build a new prompt in the background that the user does not see. And that prompt could look something like what you see here in this interface. First of all, next to the question, I'm going to provide information about how the model should answer. And I'm asking to use the context below. And I'm also asking only provide information that is relevant. And if you do not know, then please say so. And then I have the context underneath. Of course, as a developer, I will need to find a way to find this context in some kind of database. That could be documents on SharePoint, that could be the web, that could be a specialized database for this kind of purpose. But the important thing is, I'm retrieving at runtime, when the user is asking the question, I'm retrieving information, right? So retrieval, and then I augment the generation of the model with that data. So retrieval, augmented generation, because in the end, we generate an answer, but we do that on the augmented or with the augmented data. And in this case, the model is clever enough to see, okay, to park at Kronos, this is what you do. The other piece of context, the Microsoft information, it is not going to use. And that is something that, of course, we want to automate. Now, that sounds kind of easy. When I'm asking a question how to park at Kronos, I have to find let's say, answers to that question. I want to find pieces of text in some kind of database that give me that information. And there are several ways on how we can search, but let's first take a look at how we can spot similarities. And as a user or a human user, that's actually quite easy to do for us. If we look at these three sentences, it's clear for us that the first two are about cloud computing. It's about computing. It has nothing to do with the weather or actual clouds. And then the third sentence is really a sentence about the weather. And we can group these directly into two groups. The first two belong together, and the third one is on its own in its own group. That's easy for us, especially when the amount of data is low. But how do we do that with a computer system? How do we find these similarities? For a computer system, it's of course not so easy to spot similar pieces of text or to find related pieces of text. Now, there are several ways on how to find related or similar texts. One way of doing so is by using vectors. So in that case, that means that we want to express the meaning of text in a series of numbers. How many, that will depend on the system that we use. And now we have to find a way to use these numbers to calculate what is similar and what is grouped together. You should bear in mind that this is just one way of finding similar pieces of text or querying for additional information for our RAG system. This is not the only way, right? Now, we're going to use indeed a series of numbers. We call them vectors. And if you look at, for example, the example vectors for apple and banana, as a human, we can see these numbers are somewhat closer together. This might indicate that these are similar things. And yeah, for us, we know that's fruit. River and lake, we can see, is further away from the numbers of apple and banana, but on their own, they're kind of close together. Yeah, we know, of course, that they are bodies of water. Now, as a developer, when you're building a chatbot assistant and you want to use RAG and vectors to find similar pieces of text, you probably do not want to build such a system from scratch. That's why we use pre-trained embedding models, and they take text as input and they output this vector, a list of numbers. The model is trained on text in multiple languages. That's interesting because that means that, for example, if your source data is in English, but you ask questions in Dutch, you will still get relevant information back. Now, of course, there are many models to choose from, right? There are open source models, you have models from companies such as OpenAI, and we often in Azure used text embedding ADA 002. That model is a somewhat older model already. There's a new version of this model out with even better performance. Now, this particular model, takes a text of a maximum 8,000 tokens as input and then outputs a list of numbers, 1,536 to be exact. So we have an array of 1,536 dimensions. It's important to realize here the limit of the 8K tokens. You can't just feed an entire large document, like a large Word document with hundreds of pages. You won't be able to feed that to this model. This is one of the reasons we have to break our documents into smaller pieces of text and then vectorize these smaller pieces of text, or chunks as we call it. Now, sometimes we get the question, isn't that very expensive, embedding all of the text we have, for example, in our SharePoint system? Well, the cost of using an embedding model is very low. This is just one example of cost here. Depending on the model you use, the cost, of course, will be different. But compared to the cost of an LLM, this usually is not something worth talking about even. When we use an embedding model to generate a vector, like in the previous one, 1,536 numbers within that vector, we can actually plot this vector in this multi-dimensional system and then do a calculation to see how close is the query vector. For example, in my case, how to park at Kronos. I would create a vector from that question. I would then do a calculation to see, do I have other vectors in this multi-dimensional space that are close enough to that query. Now, it's difficult for us to imagine this kind of multidimensional space, especially 1536 dimensions. But think about it, when that would be only 2 dimensions, then you would see things like this, right? And then we just have to make or find a calculation that determines how close are the other arrows, so the green ones and the orange ones, how close are they to my query vector. And we can just calculate the cosine of the angle in this case between the vectors to see how close they are. And the closer you get to 1, the closer the vector is to your query vector. So in my case here, I can see visually that if I say give me the 2 closest pieces of text or the 2 closest vectors, it would be the 2 green ones. And the 2 orange ones I wouldn't include in my search results. But of course, you have to think about this at a more massive scale, when you could have hundreds or thousands or even millions of vectors, and you are going to calculate the similarity, the cosine similarity between those vectors and then the query that you originally typed as a user. So that's basically how we do RAG when we use vector search here. Okay, let's put all these things together now. First of all, before you can do actual retrieval augmented generation, you have to have some kind of database that contain the pieces of text and their vectors. Of course, if you're using a vector-based retrieval system. I want to say it again here, we focus on vector-based RAG, but that's not the only way to do RAG. You could also do RAG, for example, and just do a keyword search. Or you could just do a Bing search or a Google search and include those results in your RAG system. But in this case, we focus on these vectors. So we have our documents somewhere in the first step. These documents might be in SharePoint or some file share, that doesn't really matter. But typically these documents, they are too big to create our vectors from. So what we have to do is we first have to convert these documents to text, because LLMs work with text. And then we have to split those texts into splits or chunks, as we also call them. When we have all these splits or chunks, we can create the vectors for every split. And that's where, of course, the calls to the embedding model come into play and where there's some cost involved. And then we store the vectors together with the original text in a vector store. This work has to be done in advance for your retrieval system to work. Then you build your chat assistant, where a user types in a query. That's a third box here. The user types in the query, in my case, how to park at Kronos, but we don't send that query as a prompt to the LLM. We're first going to retrieve relevant documents from our vector store. And that's where these cosine similarity calculations come into play. So we have all these splits with all these vectors. We're going to select from these splits, we're going to select the most relevant pieces of text. It's important to realize that these can come from different documents. When we have found relevant pieces of text, we're going to take them. We're going to build a new prompt. You have seen that in one of the earlier slides. We're going to tell that prompt, hey, here's the original question. This is what you have to do with the original or extra context we are giving to you in this prompt. And then the LLM can answer based on the hopefully relevant pieces of text that you found during the retrieval phase. Although vector-based RAG is used in most chat assistants, there can be some issues with it. First of all, I talked a lot about finding relevant pieces of text, but that's actually not what you do, right? You are searching for semantic similarity. That is not the same as relevant pieces of text. The system doesn't actually know what is relevant and what is not. It has no understanding, it has no concept of relevance. Now, what we're doing with our cosine similarity, we're actually asking for the nearest neighbor, right? So when I have a query and that query has a vector, I'm asking for the, let's say, the 5 nearest neighbors to that query vector. But the nearest neighbor can live very far away from you, right? You might not have information about the question the user is asking you, and then you will still get a result from your similarity query. And there are ways to optimize that, but it's not always that easy. There's also a lack of context. For example, you have all these different pieces of text, but there is no relationship between these pieces of text. The system does not know anything about how they are related. So this lack of relationships, how things are connected together, is something that might be of importance when we're building something like a chat assistant. And of course, when you think about it, when we talk about knowledge graphs, that might be something where we can solve a couple of issues. There's also quite a big impact of the document structure. The way your document is structured might give you good results in RAG or not. And we want to break that a little bit, and using a knowledge graph might be a solution there as well. It's also kind of difficult to explain why content was actually retrieved, because it all depends on the embedding model and the kind of similarity metric that you're using to select pieces of text. So there are all kinds of issues here, and I would say mainly the lack of context, the lack of knowing what is relevant, the lack of relationships. That is something that is the biggest issue. It's just a collection of pieces of text. They all have vectors, and you just select nearest neighbors to your query based on these vectors. And there are ways to improve on that. Now we have seen how vector-based RAG works and some of its drawbacks. Let's take a look at knowledge graphs and just the basics. The knowledge graphs we are going to work with look like this. Now, without having to explain the theory behind knowledge graphs, you can directly see what it's about. What you see here are, first of all, entities of different types. For example, we have an entity of type person, entity of type country, entity of type organization. And then we have, between these entities, or nodes as we call them in the graph, then we have relationships between the different entities. And these relationships, they can have properties, and they are labeled as well. So for us, it's very easy to see, oh yeah, indeed, Bill Gates is an American citizen. He is married to Melinda Gates, and she is married to Bill Gates. He founded Microsoft, but the current CEO is Satya Nadella. So what we are thinking of with knowledge graphs is to have our information encoded into a system like this, and then we can ask queries based on the information you see there. And of course, there's already a big advantage over the basic vector-based RAG system, is that here you clearly have a structure, you have relationships, right? And you can use that to your advantage to do all sorts of, let's say, interesting things for your chat assistant or other application. Now, the question, of course, is, where do we store this information? Like in the previous section about vector-based RAG, we used a vector database, optimized to store vectors, millions of them, and then do these similarity calculations. Well, when you have a graph structure, you also have to store that somewhere. And that could be a graph database. And there are several graph databases. I've only put two here, because if you're an Azure user, you probably know that Azure Cosmos DB for Apache Gremlin allows you to store data as graphs. It's commercial license, of course, and it uses a query language, a specific language, the Gremlin query language, to ask questions about the graph that you store within Cosmos DB. And then, of course, very well known, open source, but with commercial licenses available, is Neo4j. It uses a different query language, the Cypher query language, and it's very widely used. Now, to give you an example of a query, in this case a Cypher query, I want to find, for example, the CEO of Microsoft, which is an entity of type company. And here you see a potential Cypher query here that does that exactly for you. Now we could build a retrieval system that is basically taking the user's question, for example, how to park at Kronos, and then tries to create a cipher query for that. Of course, you'll have to tell the prompt about the structure of your knowledge graph so that it can create the proper query. And this is just one way of using graph databases directly through their query language. Now, in a moment, you'll see we're not actually using this approach within the Microsoft GraphRAG solution, but know that is possible. Let's now turn to GraphRAG in general. So using or creating a retrieval augmented generation system based on graphs. So what we're going to do here is we're going to use a knowledge graph, I think that is clear, to retrieve content to feed to the prompt instead of basically just finding relevant pieces of text based on some similarity metric. Now, this can optionally use vectors to find entry points in the graph. So this is where it becomes interesting. You're basically combining these similarity scores and vectors with graphs and knowledge graphs. For example, when I'm asking the question, how do I park at Kronos? I'm trying to find nodes in my graph that are related to parking and then work my way up from there to find the relevant information about parking at Kronos. Again, this is an optional thing, but you'll see that in the Microsoft GraphRAG approach, this is an approach that is used here. Now, the vector store could be separate from the knowledge graph store. Or if you're using something like Neo4j, it can be integrated. And Neo4j can store vectors as well together with the nodes and the text information that's within that node. Then when you get results from the graph, you can also do re-ranking with a graph-based re-ranking algorithm. But also optionally use the graph to create communities and community summaries. And that's also an interesting feature, which is part of the Microsoft GraphRAG approach. So we'll also look at that in a moment. But GraphRAG in general basically means any kind of RAG-based system that uses graphs, knowledge graphs, and we can optionally combine this with vectors to find entry points into the graph. Let's take a look now what the steps are to create a GraphRAG solution. And the first step, and probably the most important step, is you have to create the graph. If you just have documents that you want to use, that's not so easy, and you really don't want to use a manual approach here if it's about large amounts of text. The typical approach followed here is to create the graph with an LLM, right? And that's also the way that, for example, Microsoft's GraphRAG solution is taking. And you'll also find that things like LangChain and so on, they have systems as well in place that can create graphs for you based on initial text documents. When you have the graph, you can then choose the GraphRAG approach. As I said earlier, you could try and convert plain text to a query, like a cipher query, and then work from there. Or, as I just explained, we can also work with vectors to find entry points into the graph and then work from that starting point. Different ways, different approaches. Then, of course, we're going to manage and analyze the running app and adjust as needed, as we always do. Now, let's take a look at the Microsoft GraphRAG solution. This solution is going to build the graph from documents. So as I stated, we're using an LLM, and then we're going to use the graph in queries. Now, you should realize that Microsoft GraphRAG is not a part of Azure. It's just an open source project that you can use and modify the way you like. And it's based on the paper From Local to Global, a GraphRAG approach to query focused summarization, right? You should read that paper. I'm not going to go in more detail about that paper. It's an interesting read to understand the thinking behind the GraphRAG solution, and you'll find more information about the GraphRAG solution itself, of course, on GitHub. Now let's focus on graph creation and a little bit more with the Microsoft GraphRAG solution. What we're actually going to do is we're going to take our documents and we're going to chunk them into little pieces again. From these chunks, entities and relationships are extracted. So things like persons, organizations, and so on. They're extracted, and then the relationships between these entities are extracted as well. This is all done with an LLM, and there's a specific prompt involved that you can tune to do your own proper entity and relationship extraction for your domain. Then when you have all these entities and relationships, we just call them element instances, we're going to create summaries for all these elements. So an LLM is going to take a look at the text that is actually used to create the elements, and then it's going to create a summary for that element. For example, if it finds a person and that person is Bill Gates, it will create a summary about Bill Gates and attach that to the element. That's to give the LLM later more context to use in the RAG approach. Now, we could stop there, but the Microsoft Graph solution or GraphRAG solution also goes a step further. It uses the created graph and the elements in the graph to create what we call communities that are different entities that belong together within the graph, and they use some kind of community detection algorithm to do so. Now, when you have these communities, you can take the text within the elements of these communities and then generate community summaries. For example, you detect a community about certain things happening in a certain organization. Well, then you have some pre-generated community summary about multiple entities that belong to this organization. These community summaries are later used in something which is called a global query, and it's used to provide global answers. And I'll demonstrate that more later, what that specifically is. This is something Microsoft added in their GraphRAG approach. They use the graph to create these communities, right? So that's kind of unique and novel, and something that they are doing in this project. Okay, that's the graph creation. But of course, we have to create our graph, and we do that during, let's say, an indexing process. Now, to actually install it, I won't show you how that's done. It's very simple. You just have to have a Python environment. You run pip install GraphRAG to install the GraphRAG package. And then you go to some folder, and there you run this command here to initialize the GraphRAG indexer. Within the folder where you ran this command, you then create a folder called input, and you put your txt files in there. You will find that the init approach here creates a .env file. In the .env file, you can set your GraphRAG API key that can be your OpenAI key. And then to run the pipeline, which basically means we're going to chunk these texts and create a graph from it, we just run Python GraphRAG index. Now, the time that this will take depends, of course, on the input data, the model, and the chosen chunk size. The default chunk size is 300 tokens. If you make that wider or larger, like 600 tokens, for example, it will go faster. But the drawback here is that it might be, or the entity extraction process might be less precise. So in my example, I'm going to leave it at the default chunk size, which is 300 tokens. So now you're probably thinking, well, this is great. Microsoft is creating a graph for me and probably is storing that graph into a graph database. Well, I have to tell you, a graph database is not used in the Microsoft open source GraphRAG solution. Actually, data is stored in two places. As I said earlier, embeddings or vectors are used to find entry points in the graph. So the text chunks that were created and the vectors that are calculated from those text chunks, they are stored in an embedded LansDB vector database. That's just a few files on the file system. There's nothing that you have to run to make this work. And then the rest of the data is just stored in a collection of Parquet files. For example, here, when I ran my indexer at a certain date and time, then the artifacts folder contains all these Parquet files. For example, here, this file contains the list of extracted entities. With a Parquet viewer, you can simply open this up and see all the entities that were extracted. Now, in the meantime, after this GraphRAG open source solution was released, lots of other people and organizations have created implementations of this GraphRAG solution. And one of them is from Neo4j itself, and they have an implementation of this Microsoft GraphRAG approach where the actual graph is stored in a Neo4j database. And to create the graph, they're not using the Microsoft approach here, they're using LangChain LLM Graph Transformer. So take a look at this article. It's quite a lengthy one and technical one, but quite interesting to see and to also understand even more about how this approach actually works. Even when you deploy this solution, the Microsoft GraphRAG solution, to Azure, because there's a template within the repository to do that, even in that case, the Parquet files are still used. They will be stored in a blob storage. Microsoft is not using, for example, Cosmos DB and its graph capabilities when you deploy this as an Azure project. That might come later, but for now, that's not the case. The title of this session includes GPT-4o mini. There's a reason for that. Well, first of all, indexing, you have to know, can be very costly. A lot of LLM calls are made. Now, GPT-4o mini is first of all fast, so indexing will take a relatively small amount of time compared to some other models. It is cheap, so the cost is easily 10 times less than previous models, but also it is still capable enough to create a good graph. And that's the reason why we switch to GPT-4o mini, and I'll show you in a moment where to do that in the configuration files. Let's take a look at the project in action. So I have a folder here, a GraphRAG folder. In that folder, I ran the init command you saw earlier. That init command will create some files and some folders, although most folders here are actually the result of running the indexing procedure. But what you do get from init are settings, basically best practice settings to get started. First of all, you get an env file. In that env file, you can set your OpenAI key or the key to access Azure OpenAI. And then there will be a settings.yaml file. There are lots of settings in this file that we will not go into, but at the top you will see, for example, the LLM information. So this references the API key that's basically in this env file. The type should be OpenAI chat or Azure OpenAI chat, depending on the environment that you use. And here we also switch the model. I think the model that they used before, or the default, was GPT-4 Turbo or something. I switched this to the model name, in this case in OpenAI, which is GPT-4o mini. All the rest, like model support JSON and max tokens, I just leave it at the default. Be aware that if you do use Azure OpenAI, you have to also fill in some things like the API base, the API version, and the Azure deployment name as well. That's something that's required by Azure OpenAI. The next thing we need is embeddings. The reason we need embeddings, or the need to create vectors from our chunks of text, is that in certain queries in this GraphRAG approach, similarity search is used to find entry points in the graph. So we need to have some kind of model that creates these vectors for us. Here you see I'm again using simply OpenAI, not Azure OpenAI. The type is OpenAI embedding, not Azure OpenAI embedding. And I'm using not the model I referenced earlier, that's an older model. I'm using here a newer model, text embedding 3 small. These are smaller vectors, but they are just as effective as the larger ones in this case. So that's embeddings. And if you go a little bit down here, you also see that we have settings to control the chunk size. So here you see the default chunk size is set to 300 tokens. You can make this higher if you want, but again, it might be less precise, the creation of the graph. So I'm going to leave it at size 300 with an overlap of 100. We can also see that we are using files on the file system, and we're also using text files as input. And indeed, this means that this requires, in this case, a folder called input, which is here, and I put some text files in this. Simple 2 books basically, 1984 by George Orwell, and then we also have A Christmas Carol in there. So 2 books are part of the input, right? And they're in text format. There are many other settings here that have to do with how do we do entity extraction. And for example, entity extraction is done by using a prompt. Well, the prompt is referenced here in the prompt setting, and you can find that prompt here in the entity extraction prompt. It's quite an important prompt because if you have your own documents and you want to extract your own custom entity types, you will have to adjust somewhat how this entity extraction prompt works, and also here, for example, specify the entity types that you want to extract. So you will see that the indexing I'm running later, there will be a lot of entities like organization, person, geo, event, and that's something we can take a look at later here. So lots of settings, too many settings to go into, but this is where you would basically modify the default settings and experiment a bit with what works best in your scenario. Let's take a look now at the indexing process. So within the folder GraphRAG, I just have to start with this command here, python-m GraphRAG index, and then the GraphRAG index process will start. Now I'm not going to go through everything that this index processing does. What you'll see here is, we create, first of all, from our text files, we create these smaller pieces of text. We call them text units. We have 917 pieces of them. And from those units, we're going to create the entities for the graph. We're also going to find relationships between these entities in the graph, and we're going to store them in files. A lot of things are being done here. Note that this process can take quite some time because a lot of LLM calls are involved to do all of this work here. In my case, for the 2 books I have in my input, it takes around, I think, 5 to 7 minutes. The cost, because of a GPT-4o mini, is relatively low. I don't think it's more than $1 or €1. Might be a little bit more, but certainly not more than that. Where in the past, with other models, it could easily be something like €10 or something for simply these 2 files, which are like 800 kilobytes in size in total. So that's quite a difference in cost. Now, when this is finished, what we get is the following. First of all, we'll get a folder in the output folder here, the folder with the most current date and time, so the 21st, well on time here. And now we have an artifacts folder. And the artifacts folder in the Parquet files contain all the information that was generated during this indexing process. For example, I can take a look at my final entities Parquet with the Parquet viewer. And then you'll see here that if we make this a little bit bigger, we will see that indeed we have our entities here. For example, I can see we have an entity which has a name called George Orwell. The type of the entity is person, and that's the default person, event, geo, and so on. These are default entities which are extracted. You can adjust this and have your own entities. And then also the description generated by an LLM for this entity. So all these entities in the graph have a text description. That description is vectorized. So we can also do a search first, a similarity search based on these vectors, find certain entry points in the graph, and then work our way through the connections from there. So if I want to ask a question, for example, like, let's take a look, who is here? Winston Smith. What are the characters that Winston Smith interacts with? Then I'll find Winston Smith in the graph, and then takes a look at connected entities, what kind of characters or persons Winston Smith is interacting with. And we'll see that later. Right? So all of these files, everything, as I said, is stored in Parquet files. It's not stored in a graph database. Great. Now we have this graph, we can start doing queries. So let's take a look at how that works. There are 2 types of queries with this GraphRAG project. The first one is a local query. Local query, as opposed to global query, is going to find entry points in the graph and then work from that entity that it found, evaluate the relationships, and give you information back about that. For example, this is good for questions like, I want to know about this specific thing, and give me related information about that thing. If we were to use, instead of this GraphRAG approach, if we were to use a standard vector search based approach, well, it might find pieces of text about Winston Smith, but it might not necessarily find all the pieces in the book, all the pieces in the text that contain the people that Winston Smith interacts with. So although you might have some results with that vector-based approach, the approach with a graph underneath should be better and should be more complete. And if we look at what the actual result is, and by the way, you can see this is not for end users, right? It's a lot of, let's say, debugging information that is being shown to you. The response is here that, okay, I'm giving you an overview of Winston Smith. It's clear that we know what Winston Smith is about, character in the book 1984. And then you have like key interactions. And here we clearly see that we found an entry point in the graph about Winston Smith. Yeah, you can see here what he's talking about, the entities 5 and 8. These are Winston Smith related entities. And then we go and find in the graph connected entities. And in this case specifically, people that are connected to Winston Smith. And now we have a somewhat more exhaustive list about people that he interacts with. Maybe not all, but we do have quite a long list. And this is certainly not guaranteed if you just feed the 1984 book and do standard vector search. This is certainly not guaranteed that you get this result back. So we get Julia, we get O'Brien, and so on. Plus also, and that's important to explain where the data is coming from, we see that, hey, this is actually entity 346 in the graph. In a real application, you could then have a link to that entity and potentially let the user explore related entities to Julia. Now we come to the other type of query, which is a global query. And this is something that standard vector search is really not good at. Because if I'm asking what are the top themes in 1984, what's going to happen? Well, it's going to vectorize this question, and it's going to look for related pieces of text that are close to this question vector. And in the book itself, there is no real block of text that describes what the top themes are. The top themes, of course, are described throughout the book. And this is something that this project aims to solve as well by introducing a special type of query that requires a graph to enable this, and that is this global query. Now, by the way, one small remark here. 1984 is a well-known book, so if you were to ask your LLM what are the top themes in 1984, it wouldn't know that, of course, because it can answer it from the weights. But think about this in a business context where you use data that the LLM has never seen. So let's see what happens when I ask this question and I'm saying, hey, I want to do a global query here. What happens here is that we are not really going to use the same method as with local queries. We're going to use the community summaries that were generated. Remember, we have all these entities and there's some kind of clustering algorithm or a grouping algorithm that puts several of these entities together in communities and then creates a community summary for each community. Well, what this is doing, it's going to take these communities and it's going to ask the question, what are the main themes to each community? All of those questions or the answers from each community report are then brought back together to answer a final question. Okay, give me now the main themes of 1984. And that's how these global queries are supported. And that works quite well because, of course, the community reports contain a lot of information packed together about related entities. And when you ask multiple of these communities about what are the main themes and then bring it all together, you really have like a broad response over the entire document set. And if we look what it is doing here, we can see that indeed it says, well, in 1984, we have several themes. Of course, totalitarianism being the most significant. And then he says, okay, here are the different themes. And we have like totalitarian control with, again, links to the community reports. Every report is an entry in a Parquet file and has an ID as well. So in this case, we don't use the entities directly. We work from the community reports that are stored in the Parquet files as well. So the control, manipulation of truth, personal rebellion, and so on. Now, because of the fact that we also limit the amount of tokens being used to generate the answer, this could be somewhat longer, but I think you get the idea. The global type of query is used to ask questions that are global in nature, global in scale, and that's something that the graph is used for, to create the communities and then to create the community reports that this global query works with. Be aware these global queries, yeah, of course, there are multiple LLM calls used. It can be easily something around 10 LLM calls. You have to first question all the different community reports, get an answer back, which is created by the LLM, and then a last question to all the intermediate answers. So there is quite some token usage as well. I think for this question, I think around 150,000 tokens are being consumed to just answer this question. So again, it's important here to work with lower cost LLMs that are still, of course, quite capable to give you, let's say, the lowest cost possible. There's also quite some latency involved as well. And the user will have to work or wait quite some time before the answer is generated. Okay, now that you have seen standard RAG and we focused on vector-based RAG, and you've seen what a knowledge graph can do, especially in this project with local and global queries, what does that mean for your projects? What do you use in your projects? Well, I think for most chat assistants today, you should always start with standard RAG, right? And instead of vector search only, you can combine that with keyword searches into a hybrid search. You can add web searches or all of these different things together to provide the best context possible to your chat assistant. Now, if that doesn't work, or the customer has specific requirements where you think a knowledge graph can help, then of course do add a knowledge graph. You don't have to use a knowledge graph on its own. You can combine standard RAG with knowledge graphs and then use one or the other depending on the question that the user asks. The knowledge graph, of course, will help you in being more precise about asking questions about a certain entity and then using relationships to other entities to really have good detailed answers and to provide also information to the user why the answer was given and where the answer comes from. And as always with LLMs, it's very important to evaluate the approaches. We have seen, for example, implementations where simple knowledge graph approaches are not necessarily better than standard RAG. So you always have to evaluate with some evaluation framework to see, okay, what works best, what gives me the better answers, what scores best. Okay, so that's it for this presentation. I hope you enjoyed it, and maybe I see you again some other time. Thanks for watching. Bye-bye.